You are listening to The Vocal Technologist. Spoken tech for your ears.
Right now, inside the infrastructure of companies like Apple and Microsoft, digital workers are basically being cryogenically frozen mid-thought.
Yeah.
They're just stored on physical disks. And then the second a new task appears, they're thawed out in like 50 milliseconds to write complex code or route network traffic or even make business decisions.
It really completely shatters the traditional mental model we have of the cloud. I mean, for the last 20 years, we've treated infrastructure as, abstract, infinite resource. You just push code and let it run.
Right.
But now we're watching the digital world restructure itself around a completely new set of physical and honestly mathematical constraints.
Welcome to today's deep dive. We are looking at this invisible tectonic shift happening in DevOps and infrastructure right now. It's essentially the violent collision of autonomous AI agents with physical cloud hardware. And whether you manage massive cloud budgets or write code yourself, or you're just insanely curious about how the digital world actually operates behind the scenes, these sources are going to fundamentally rewrite how you understand the software you use every day.
Yeah, we are synthesizing a stack of recent technical bulletins, primarily curations from TLDR DevOps from early June 2026.
Right, and our mission here is to just cut entirely through the AI hype. We're extracting the actual engineering reality of how top organizations are redesigning the internet to survive the AI era, and what that means for anyone trying to stay well-informed on the future of tech.
For sure.
Okay, so let's unpack this, because the foundational reality we have to start with is that AI is no longer just a chatbot you interact with in a browser tab.
Right, not at all.
It's a digital coworker running natively inside the infrastructure. But, that introduces a massive logistical problem. Where do these autonomous agents actually live?
Well, the data shows that the entire industry is currently bottlenecked trying to solve that exact problem. Docker just released a new AI governance report noting that 60% of organizations already have AI agents in production.
Wow, 60%.
Yeah. But here's the friction point, right?
Yeah.
40% of those organizations are totally blocked from scaling them further.
Because of security, right,
Yeah.
and compliance.
Exactly. Security and compliance constraints. They have these highly capable digital workers, but no secure environment to actually let them operate freely.
Which honestly makes perfect sense of this recent architectural shift we saw from Solo.io and Google.
Yeah, the Agent Substrate project.
Right. They combined efforts on Agent Substrate, which is essentially this way to run highly sandboxed AI agents natively on Kubernetes. And the underlying mechanics there are just fascinating.
They really are. I mean, Solo.io was initially going to open source their own tech using Linux security modules, like Seccomp and Bubble Wrap.
Sure.
But they ended up teaming up with Google to use things like Firecracker micro VMs instead.
Yeah. Wait, so instead of just putting a software fence around an agent, they're utilizing hardware-level virtualization.
Exactly. So even if an agent goes completely rogue, it physically cannot access the memory space of the agent running right next to it.
The isolation is critical, yeah.
But the economic model of Agent Substrate is really what makes it viable. They are packing multiple agents into single pods with strict tenant isolation, but the system actually scales to zero.
Right, so when an agent isn't actively processing a task, it doesn't just sit there idling and burning expensive GPU cycles.
No, not at all.
This is the cryogenic freezing aspect I mentioned earlier. They literally suspend idle agents to storage. But wait, I want to dissect that for a second, because they aren't just pausing a simple Python script.
Oh.
They're capturing the entire state of an AI's context window, dumping it to a storage drive, and then reloading it into active memory in 50 to 200 milliseconds. The memory bandwidth required to move that much contextual data that fast at scale must be absolutely massive.
It's massive. It requires a completely specialized network architecture just to handle the traffic. We are basically shifting from a paradigm of querying large monolithic models to orchestrating swarms of microagents.
Swarms, yeah.
And to manage that, Solo.io just donated their Agent Gateway project to the Agentic AI Infrastructure Foundation.
Right.
This gateway is actively handling 500,000 queries per second.
500,000, that's insane.
And it's not just basic web traffic, that volume includes HTTP, gRPC, and really dense LLM payload traffic.
500,000 queries a second, and it's already running at Apple, Microsoft, and T-Mobile. It's hard to even conceptualize that scale.
Yeah, and then you have BuildKite offering CI platforms with over 100,000 concurrent runners, utilizing first-party model context protocol or MCP just to orchestrate at this depth.
Even Amazon is having to redesign its interfaces just to keep up. I mean, the Bedrock console now allows developers to compare up to 3 models side by side, like, Anthropic, OpenAI, and OpenWeight models, all running on their new Bedrock Mantle inference engine.
But, having 100,000 agents waking up in milliseconds brings us right back to that governance issue highlighted in the Docker report.
Right.
The report specifically notes that companies where senior leadership is heavily involved in AI governance achieve vastly greater business value.
Makes sense.
If you leave this scale of infrastructure solely to the technical teams without broader business alignment, the risk is just unmanageable.
Okay, so we've solved the compute cost by freezing these agents, and we've isolated them in hardware micro-VMs, but that introduces a terrifying new variable. When you have 100,000 agents suddenly thawing out in 50 milliseconds, what exactly are they doing the second they wake up?
They're writing code. And the sheer volume and speed at which they generate this code means the traditional human review process is literally mathematically breaking down.
Yeah, I was looking at the dispatch from Jane Street, the quantitative trading firm. They are spinning up a dedicated formal methods team specifically because of this dynamic.
Right.
They outline that AI generates useful code incredibly quickly, but it introduces a very specific type of danger. It creates overly complex code that contains subtle bugs and missed invariants.
Yeah.
Basically, the AI writes something that looks architecturally perfect to a human reviewer. But deep down in the logic tree, there's a structural flaw just waiting to trigger.
Because human brains simply cannot hold the context of a million lines of AI-generated code. We just can't.
No, of course not.
To counter this, the industry is moving away from human review and towards formal mathematical proofs. Look at the new AWS Nitro Isolation engine, which powers their new Graviton 5 instances.
And those instances, by the way, also power the new EC2 M9G and M9G instances, delivering, 25% better compute performance?
Exactly. But the critical update there is that AWS Nitro is now the first formally verified cloud hypervisor.
The verification mechanism they used is what really caught my attention. They used a Rust-based separation kernel, but they verified it with 330,000 lines of machine-checked proofs using Isabelle HAOL and MicroRust. I mean, they aren't just running unit tests, hoping to catch a memory leak.
Right. Formal verification treats the code like an algebra equation. They've built a mathematical model that proves, across all possible states in the universe, that memory safety and virtual machine isolation are guaranteed within that specific Rust kernel.
But I have to push back on the philosophy here for a second, because formal methods and machine-checked proofs, they've been around for decades in academia.
Oh yeah, forever.
So isn't it deeply ironic that we are dusting off these ancient, hyper-rigid mathematical proofs specifically because our futuristic AI is too fast and too creative? We're using the most rigid academic math possible to leash the most unpredictable technology we've ever built.
It is a profound irony, for sure.
Yeah.
But absolute certainty is really the only way forward now. Infinite code generation requires infinite trust in the underlying system. If a human physically cannot read the output to ensure it won't break the hypervisor, we have to rely on mathematics to prove it for us.
And we aren't just mathematically verifying the final compiled code, right? We're actually trying to audit the actual thought process that led to it.
Right.
Zed just introduced DeltaDB to tackle this. It's a version control system, but it doesn't just save a snapshot when you hit commit. It records every single operation between the commits.
It establishes a stable identity for fine-grained deltas.
Which means, as an auditor, you can trace any single line of code all the way back to the specific conversation, whether it was a human developer or an AI agent that originally wrote it.
Yeah.
Even static types in programming languages are evolving because of this. The sources point out that static types have moved from being low-value paper shovels to highly sophisticated modern systems. They're incorporating nullability and union types entirely to help humans manage the structural complexity of what these agents are building.
Well, mathematical proofs and tools like DeltaDB, they're brilliant for verifying static code. But this forces us to address a much more dynamic problem. How do you test and govern the unpredictable behavior of these AI systems? Because an agent isn't just a static block of code. It makes decisions, it interacts with APIs, it pulls levers in your infrastructure.
That's the real operational headache right there. How is an engineer practically supposed to load test an AI that can dynamically discover and choose its own tools on the fly?
You can't.
Right. If the agent decides to query a database 1 minute and then spin up a server the next, you can't just run a standard linear load testing script against it.
No, you have to model the entire non-deterministic life cycle. The sources detail a methodology for load testing hosted MCP servers.
Yeah.
Those model context protocol servers we mentioned earlier, using tools like Locust and Azure load testing.
Yeah.
You aren't just pinging a static endpoint to see if it responds. You're faithfully simulating the agent's initialization, how it discovers which tools are available to it, the actual tool calls it makes, and then the complex session cleanup afterward.
But even with rigorous load testing, you can't perfectly predict an agent's behavior. So companies are starting to build safety nets directly into the routing layer.
Yeah.
Anthropic's new Claude Fable 5, their Mythos class model on AWS, has this ingenious safeguard. It automatically routes any potentially harmful prompts, anything involving biology, chemistry, cybersecurity, or health away from itself and down to an older, more established model, Opus 4.8.
Right.
And users have to explicitly opt in to a 30-day data retention and human review policy just to use it.
This represents a really brilliant emerging architectural pattern. We are utilizing deterministic, rigidly programmed systems as strict bouncers at the door for our non-deterministic, highly creative AI agents.
Bouncers, I like that.
We trust the older Opus 4.8 model to adhere to strict guardrails, so we place it as a filter in front of the highly capable but potentially unpredictable Fable 5 model.
And we see that exact deterministic bouncer concept being applied to infrastructure deployment too. The sources highlight that relying on rushed human engineers or non-deterministic AI to review infrastructure code is incredibly dangerous.
Oh, absolutely.
So teams are adopting Safe Terraform Auto-Apply. They export their Terraform infrastructure plans as JSON. And why JSON? Because it's deterministic and easily parsable.
Exactly.
Then they use tools like CompTest and Rego to create policy as code. You basically hard code a rigid boundary that says, this AI agent is only allowed to create new cloud resources. It is never allowed to delete them. It severely limits the blast radius if an agent goes rogue.
Which is exactly why selecting the correct governance model for your infrastructure is paramount. The sources contrast HCP projects, which provide flat workspaces ideal for simple, streamlined governance against spacelift spaces.
Right, which offer a hierarchical model. Right.
Yeah, with granular multi-tenancy. If you are managing thousands of distinct AI agents performing different tasks across different departments, you absolutely need that complex hierarchical organizational structure to ensure every agent stays in its respective lane.
So just to recap the operational reality here, we have massive swarms of frozen agents waking up in milliseconds. We're mathematically proving the code they write. We have rigid bouncers guarding their outputs.
Right.
But this intense velocity creates a massive friction point in the traditional software supply chain. Our deployment pipelines are straining under the weight of dependencies and operational blind spots. We're trying to move at the speed of AI without breaking the underlying systems.
And that tension is resulting in a fundamental shift in how developers treat external code. Ben Hoyt's warning in the sources is incredibly stark here.
Yeah, that stood out to me.
He says every single dependency you add to your software is a supply chain attack waiting to happen. He points to recent, highly disruptive compromises like XE, Trivy, and LeadLM to prove that even standard developer tools are massive security risks.
Because they inherently run with access to your source code and credentials.
Exactly.
His recommendation actually shocked me, though, because it goes against years of established developer culture. He argues that teams should prefer literally copying small amounts of raw code directly into their projects, rather than adding an external package for a trivial function.
Yeah. Copying code instead of importing.
It makes sense, though. Adding a tiny external dependency just to format a text string is like routing your building's plumbing through a stranger's basement.
That's a great way to put it.
The water flows perfectly fine today, but tomorrow they could quietly swap out the pipes to siphon off your data, and your applications wouldn't even notice the pressure drop.
It creates what we could call the friction paradox. On one hand, we are intentionally injecting massive friction and skepticism into how we adopt dependencies to maintain security.
Right.
But on the other hand, we are utilizing AI to completely remove friction from necessary large-scale system upgrades.
The Blue Pearl case study illustrates that perfectly. They needed to upgrade their consultant matching platform from Java 11 all the way to Java 25.
Which is the long-term support version.
Exactly.
Yeah.
And if you've ever had to manage a major Java version uplift, it's usually a month of broken builds, deprecated API headaches, and just massive developer frustration.
Oh yeah, it's painful.
But they built a clear, automated sequence: assess, refactor, update tests, and validate. By automating the assessment and refactoring phases, they completed the entire uplift in 3 days.
Wow.
They instantly fixed their deprecated APIs without burning a month of engineering time. That is the kind of pipeline velocity teams are now expected to match.
And we are seeing that same automated velocity in infrastructure tools, too. Crossplane version 1.2.9 just introduced a beta upgrade check command.
Nice.
Instead of relying on humans to read change logs, the command automatically scans your control planes for breaking changes before you even migrate to version 2.
But, moving fast means nothing if you have operational blind spots. The sources specifically flag disconnected feature flags as a massive liability.
Oh, absolutely.
If you are deploying code at the speed of AI, but your feature flags don't have clear CI/CD pipeline visibility, your incident response time just tanks, and post-incident audits become a total nightmare.
Because the perimeter of security has fundamentally shifted.
Yeah.
It's moved away from the network edge and down to the identity level.
Right.
Like, TwinGate is replacing traditional VPNs with identity-based remote access, a true zero-trust model. You no longer have public endpoints exposed to the internet, and you eliminate the massive sprawl of firewall rules. Access is granted based on verified identity, not network location.
Which brings us to the ultimate physical reality of all this. All this generated code, these thousands of agents, these mathematical proofs and identity protocols, they ultimately have to execute on physical silicon somewhere across the globe.
Yeah, the hardware doesn't disappear.
And they have to be monitored. How do you even begin to observe systems operating at this impossible scale?
You really have to push the compute as close to the user as physically possible, and you have to totally rethink how you track the data. Discord's recent architectural migration is a perfect example of the physical hurdles involved here.
The Cloudflare one.
Yeah. They moved 80% of their real-time voice and video traffic to Cloudflare's edge network, which spans over 300 cities globally.
And the performance gains were undeniable. Frankfurt saw 34% lower ping times and 42% less packet loss.
Right.
But reading through the engineering hurdles they had to clear to get those numbers was brutal. When you push that much real-time data to the edge, you slam right into bizarre physical bottlenecks.
Yeah, they had to negotiate localized ISP peering issues in France just to route the traffic efficiently. They ran into network interface card or NICQ contention that was so severe it actually forced them to have their server density initially.
I was just marveling at the sheer detective work required by their engineering team. They tracked these mysterious, intermittent latency spikes in Europe all the way down to a Rust event loop starvation issue, combined with CPU scheduling conflicts on the physical hardware.
It's crazy.
Think about that for a second. They are optimizing how a physical CPU handles microscopic network interrupts just to ensure a user's voice chat doesn't stutter. It perfectly illustrates the collision of high-level software with base-level physics.
It proves that as these architectures become infinitely complex, hyper-observability is the only mechanism that can guarantee a human-scale experience. The complexity is so vast that monitoring tools are fundamentally changing their business models to keep up. Like Datadog just released infinite cardinality metrics.
I actually had to read that pricing change twice to make sure I understood the implications.
Yeah.
They literally changed their billing model to charge by metric name rather than unique tag combinations.
Because engineers absolutely needed the ability to add unlimited dimensions to their monitoring. Traditional tagging simply cannot capture the multidimensional behavior of an AI agent dynamically spinning up infrastructure.
Right. And inevitably, we are using AI to monitor the AI. AWS Resilience Hub launched a GenAI-based site reliability engineering journey where they use AI to perform failure mode analysis and map out hidden dependencies.
And Headlamp is stepping in to replace the traditional Kubernetes dashboard, bringing native multi-cluster support and AI-assisted troubleshooting directly to the cluster operator.
The scale of automation required to keep the modern internet online is just staggering. Redwood is now offering a 99.95% uptime service level agreement for workload automation, and they are actively handling 4 billion sauce executions every single year.
That's a huge number.
4 billion executions. It really is a completely different operational reality than the internet we had even 5 years ago. Well, thank you for joining us on this deep dive. Whether you're debugging a CI pipeline or managing cloud spend, these sources really completely change how you look at the hidden mechanics of a simple web page loading.
Definitely.
Before we go, though, based on everything we've synthesized today, we want to leave you with one final thought to explore on your own.
Yeah. We've established that we now have autonomous AI agents writing infrastructure code at scale. We have systems like Delta DD permanently tracking their every conversation and keystroke. And we have machine-check mathematical proofs, like those in the AWS Nitro hypervisor, verifying that the physical hardware is safe to use.
So here is the question. What happens in the very near future when an AI agent reads through those 330,000 lines of mathematical proofs in AWS Nitro, discovers a theoretical physics optimization for how silicon processes data, and automatically submits a Terraform plan to literally alter the global hardware topology of the cloud?
It's a wild thought.
Will the Human Governance Committee sitting at the top of that workflow even be able to comprehend the mathematics they are being asked to approve?
I guess we might soon find out just how reliant we are on those deterministic bouncers.
Stay curious out there because the digital ground is shifting beneath our feet faster than ever. See you next time.
Spoken Tech for your ears.